Let's be real. When people hear age reversal, they usually imagine something dramatic: gray hair turning brown overnight, sagging skin snapping back into selfie mode, or 80-year-olds sprinting marathons while shouting, "I feel 30 again." But in the world of science, age reversal is less Hollywood, more molecular. It's not about looking younger. It's about becoming biologically younger, one tiny, stubborn biomarker at a time. And the truth is, we may be closer to that reality than most people think. First, let's clarify what scientists mean by reversing aging. It doesn't mean eternal life. Sorry, vampire fans. And it definitely doesn't mean time travel. What it does mean is slowing, halting, or even partially reversing the molecular and cellular changes that define biological aging, the kind measured by things like telomere length, DNA methylation age, and cellular senescence. These are the backstage managers of your aging process, and researchers are getting increasingly clever at bossing them around. Take telomeres, the protective caps at the ends of your chromosomes that fray and shorten with each cell division, like shoelaces unraveling over time. When they get too short, the cell hits retirement mode, also known as senescence. For years, telomeres were the crown jewel of anti-aging research, and while we're no longer as obsessed with lengthening them as we once were, looking at you, unregulated telomerase supplements, clinical work is underway. Studies like those using TA65, a telomerase activator derived from astragalus root, have shown modest telomere elongation and some evidence of improved immune function. Is it the elixir of youth?
No.
Is it an early draft of something more powerful? Maybe. Next on the checklist, cellular senescence. These are the cells that should have retired quietly, but instead stick around, inflamed and dysfunctional, secreting pro-aging signals like bitter ex-employees. Enter senolytics, a class of drugs designed to selectively eliminate these zombie cells. In both animals and early human trials, senolytics like Physodin, quercetin, and dasatinib have shown promise, improving physical function, reducing inflammation, and even extending lifespan in mice. In 2024, small-scale trials in humans with idiopathic pulmonary fibrosis and chronic kidney disease showed improved mobility and lower levels of senescence biomarkers. No, we're not handing out senolytics at Walgreens yet, but the science is walking briskly in that direction, perhaps with less arthritis. And then there's the flashy newcomer, epigenetic reprogramming. DNA methylation clocks like Horvath's clock, PhenoAge, and GrimAge have changed the game. These clocks don't just measure aging, they can track how interventions actually roll back the biological odometer. In 2019, the TRIM trial, thymus regeneration, immunorestoration, and insulin mitigation, made waves when 9 healthy middle-aged men took a combination of growth hormone, metformin, and DHEA for a year and saw their epigenetic age reverse by an average of 2.5 years. Cue scientists everywhere clutching their pipettes in disbelief. More recently, a 2023 study led by the Turn Biotechnologies team used partial cellular reprogramming, briefly activating Yamanaka factors, genetic reboot switches in lab-grown human cells, and reversed aging markers without turning the cells into tumors. This is still firmly in preclinical territory, but the concept is mind-bending. Flipping your cell's age switch without also flipping their identity into "now you're a stem cell." Diet and lifestyle interventions are also being tested with methylation clocks. A 2021 clinical study showed that a diet rich in methylation-supporting nutrients, B12, folate, choline, along with moderate exercise, sleep optimization, and stress reduction, could reduce epigenetic age by more than 3 years in just 8 weeks. Sure, it's not immortality, but reversing 3 years of biological aging while still eating real food and sleeping in your own bed? That's a pretty sweet trade-off. And on the pharmaceutical front, rapamycin, metformin, and NAD+ precursors like NR and NMN are the celebrity guests at the longevity banquet. Rapamycin mimics the effects of caloric restriction by inhibiting the mTOR pathway, and in animal studies, it extends lifespan by 10 to 15%. Human trials are ongoing, with the Pearl trial testing whether low-dose rapamycin can safely slow aging in older adults. Meanwhile, NAD+ boosters are being hyped for their role in mitochondrial repair and cellular energy, but clinical evidence in humans is still catching up to the marketing. So how close are we really to real age reversal? We're probably not going to see someone go from 90 to 40 anytime soon, unless there's a very aggressive Photoshop filter involved. But biological rejuvenation at the cellular and systemic level? Already happening. We can modestly lengthen telomeres. We can clear senescent cells. We can alter DNA methylation in ways that make cells look and act younger. The early human data, while small and sometimes messy, is pointing in one very hopeful direction. Aging is modifiable. In other words, we've stopped asking, can we live longer? And started asking, how do we turn back the clock safely without turning into a petri dish experiment or giving up tacos? So buckle up. We may not have mastered immortality yet, but reversing aging one marker at a time is no longer science fiction. It's slow, it's incremental, it's full of caveats, and it's real. Your cells are negotiable. Your biological age is increasingly a work in progress. And the future of aging might just involve a lot more lab coats, fewer wrinkles, and the shocking realization that your birthday no longer tells the whole story.